Okay, let's look at problem 5 now, which is a little different than the previous ones in that we are given 2 points, not just one, in the soil zone. In other words, one of the points is no longer an assumed point on the water table, but it's an actual point for which we have data, and we are given for both of these points the pressures measured by, say, a tensiometer. So other than that, it's a really similar problem to the ones we've had before. So the equations we're going to use, once again, are that the head is equal to the elevation head Z plus the metric potential psi. And that psi, as always, will equal the pressure, the gauge pressure, divided by the density rho times the gravitational acceleration G. Now, the first thing we're going to do for this problem is use this equation here to calculate psi for both points A and B. Remember, that is independent of the datum. So you might as well calculate these out, and then we can entertain different values of or different choices of the datum. I forgot to say that this problem is also different in that you are given the freedom to pick a datum anywhere you want as long as you can make measurements from it. And we'll go over several common choices in this solution here. But first, let's calculate the values of the metric potential for both these points. So we're going to write, let's say for A, the metric potential at A will equal the pressure at A, which is negative 3,750 pascals. Once again, we're doing this all in MKS, divided by 1,000 kilograms per meter cubed and 9.81 meters per second squared. And I plug that into my calculator, and I get a value of negative 0.382 meters. I'm going to leave three significant figures here. Okay, negative 0.382. That's pretty hard to read, but 0.3, let me just rewrite that. Negative 0.382 meters. For B, I do exactly the same thing. The pressure at B is negative 1,830 pascals divided by 1,000 kilograms per cubic meter, 9.81 meters per second squared. And this turns out to be negative 0.187 meters. So those are my two values of the metric potential, and those are independent of datum. So these are always going to be true no matter what I choose as my datum. In fact, I'm going to write them up here so that I can erase this rest of this stuff and then go through the problem with different choices of datum. But we're always going to use these two values we just calculated. The metric potential at A was equal to negative 0.382 meters, and the metric potential at B was equal to negative 0.187 meters. All right, and we can get rid of all the rest of this stuff. We don't need any of this anymore. We don't need this equation. We've already used it, and I'm just going to get rid of all this so that I can go then and talk about how we finish the problem based on various choices of the datum. All right. So let's start now, and let's say we're going to pick the surface as datum. So let's start by saying this is a reasonable choice. Let's say I'm going to pick this. This is my datum here. It's the surface. Okay, and I'll write in red the way this is going to go. So I know now I'm going to use this equation: H equals Z plus I. H equals Z plus I. This one here. And so I have psi of A and psi of B, so I need the elevation head at A and I need the elevation head at B. So these are the elevations relative to datum. So I've actually got these things written right on here because my measurements are from the surface. So I can see that point A lies 40 centimeters below the datum if the datum is the surface, right? So I can just by inspection write that Z, the elevation head of A, will equal negative 40 centimeters. It's below datum, so it's negative, and that's the same thing as negative 0.40 meters. Remember that in this equation here, both Z and psi have to be in the same units in order to add them. Psi is in meters, so I'm going to create Z in meters too. For B here, I can again by inspection say that Z elevation head of B, well, it's 70 centimeters or 0.7 meters beneath the surface, so the elevation head at point B will be negative 0.7 meters. It equals the same thing as minus 70 centimeters. Okay, so now I'm in position to calculate the head at A. The head at A will equal the elevation head at A, which was negative 0.40 meters minus, that's 400, right? Minus 0.382 meters. And so my head at A with the surface as datum will be negative 0.782 meters. My head at B will equal negative 0.700. It's actually three significant figures here, sorry. 700 meters minus 0.187 meters. And so my head at B is going to be equal to negative 0.887 meters. And I should see that my head at B is more negative than my head at A, and so groundwater will be flowing down from A to B. Furthermore, I'm going to write this up in the corner. This is water, I'm sorry, this is the surfaces datum, right? Notice that what I found is that the head at A is larger than the head at B, and by how much is the head at A larger than the head at B? So what is the difference between these two numbers? And if I subtract them, it turns out that this difference is equal to 0.104 meters. I'm just going to keep this in my pocket for a second here, okay? So using the surfaces datum, I found that water flows down and that the difference in head was 0.104 meters. Okay. Now, let me go erase everything I just did, and let's assume a different choice of datum. Okay, so I'm going to erase everything here. And now let us assume that, let's say, the water table is datum. Okay, so now that's another choice people often reflexively make, which is not a bad choice. There's datum, so this is my datum here. And let's go do our calculation. So now we need the elevation head of A and we need the elevation head of B. Okay, so let's look at A first. What is the elevation head at A? So what we want is this distance here, right? This is going to be Z of A. Notice that it is above the water table, so it is going to be positive. The entire distance from the surface to the water table is 100 centimeters. A is 40 centimeters down from the top. In other words, it's 60 centimeters, 100 minus 40, or 60 centimeters up from the bottom, right? And so ZA will be 60 centimeters positive, which is the same thing as 0.60 meters. ZB will be, well, we can use the same logic, right? We want this number here, and B is 70 meters down from the surface, and so therefore it's 30 centimeters up from the water table. So Z of B is 30 centimeters, or 0.3 meters, 300 meters. This should be 600 meters here. So head of A equals 0.600 meters minus 0.382 meters equals head of A will equal, let's see, 0.218. 0.218 meters, and head at B will equal 0.300 meters minus 0.187. If I plug that into my calculator, I get 0.113 meters. Okay, so now they're both positive, but it's pretty clear that water is going to flow. The higher values at A, so water is flowing down, just like we found before. And furthermore, the difference between these two numbers is, guess what? It's going to be 0. Well, if I actually round it properly, it's 0.104 meters. It's exactly the same thing. So this is the water table. I'm getting exactly the same difference in head, get exactly the same direction of flow. Chose a different datum. Okay, now that's another choice. I'm just going to consider a couple other choices one might make, the clever student might make to try to simplify some of their measurements here. So let's just do one more. Okay, well let's just, and what if I chose a line that goes right through B as my datum here now? Now why might I do that? Well, the reason I might do that is because that means the elevation head at B is 0, right? So anyway, let's choose that. So we're going to still use h equals z plus I. We need z of a. So z of a now will equal this distance here. And if B is 70 centimeters beneath the surface and A is 40 centimeters beneath the surface, then this difference is 30 centimeters, or 0.3 meters. That would be Z of A. Z of B, again, now this is why I chose this, was 0, because I'm sitting right on the datum. B is right on the datum elevation. So I can write, let's write it over here, h of A will equal, A is above datum, so that's positive 0.300 minus plus psi, which is minus 0.382. These are all meters. I should have written that down, meters. And if I do that using B as datum, I end up with 0.082. Is that right? Yeah, negative 0.082 meters as A. Head at B will be 0. That was easy. Minus 0.187 meters equals negative 0.187 meters. Oops, 7 meters. So once again, we can see that the head of A is larger than the head of B. Water is going to flow down from A to B, and that this difference here is, these are my choices of datum. The same thing, 0.104. So the lesson here, why I actually calculated this difference for each step, was to make the very important point that we are going to get exactly the same result in direction of groundwater flow, in the magnitude of the gradient that drives groundwater flow. All of that's going to be exactly the same regardless of which datum we choose. As long as we measure both of our heads, in this case, from the same datum, we're going to get exactly the same thing. And that is the major point I want to make from this last problem.